Okay, so today's notes are on families of functions. Our content objective is to analyze transformations of functions, and our language objective is to define terms such as parent function, transformation, translation, reflection, vertical stretch, and vertical compression, which are all the different ways that we can transform our parent functions today. So we're going to jump in by talking about parent functions, since this is sort of from where all of this stems. So a parent function is the simplest form in a set of functions that form a family. So we will learn about many different functions that you can build upon, or parent functions that you can build upon with the transformations we're learning today throughout this year, next year in math. But the examples I'm going to give you right now are ones that we're only going to do two, but the examples are linear functions, which you've seen before, and absolute value, which I'll show you in a second. But the reason I'm showing you the linear parent function is because we know linear functions, we've been working with them, and the parent function of linear functions is just the most simple form of a linear function. It has a slope of 1, an x and y intercept of 0. So it's the most standard, simplest form of a linear function. Just so you guys have an idea, like these are the most basic functions we're working with. We're applying transformations to get every other possible line you can imagine that fall into the linear function family. But this is where we're starting to build with all of these transformations. We're also going to talk about absolute value functions, along with what we've been learning about thus far this year. And those are similarly simple. So the parent function is just y equals absolute value of x. So if we label our axes, this, again, it would have a slope for each side of 1. It has a vertex of 0, 0. And it again is just the simplest form of a absolute value function that we can apply transformations to get every other absolute value function. So what are these transformations I keep referring to? Transformations are the changes made to the parent function to make the other functions in the family. So transformations are the changes we make. We can add things, subtract things, multiply, divide, and those are the changes we can make to functions like these, as well as several other parent functions we'll learn about later down the line, that can make every other linear function or absolute value function or quadratic function or exponential function that we could possibly want to work with. So I'm going to flip the page so we have plenty of space for our examples of transformations, the first of which will be translations. So translations, they slide or move the function or the graph up or down, or left or right. So we'll talk about vertical translations first. And as might be assumed based on the vertical translation title, it will move up and down. So vertical moves up and down. So vertical translations similarly move the graph up or down. And one thing I'm going to do throughout this, so I'll put a little star here, I'm going to use g of x to represent the transformed function and f of x to represent our original function, or like parent function throughout these examples. So when we're moving up or down, we'll take to get the transformed function, so our transformed function would be our original function, f of x, plus 2 or plus a, sorry, or our original function minus a. And I'm just going to do some shorthand here, but adding or a positive moves up, subtracting moves down. So in shorthand, if we're adding it, we're moving the function up. If we're subtracting it, we're moving it down. So I'm going to do a couple very quick examples of this. And for these examples, the function or the parent function we're going to use is just going to be a set of points. So we'll use 1, 2, 2, 1, 3, 2, and 4, 4. And for I'll first draw the parent function. So we have our graph here. We have 1, 2, 3, 4, 5, 6. So I'm going to plot my original points. I have 1, 2. Then I have 2, 1, 3, 2, and 4, 4. So this is my original graph. Not perfect, but bear with me. My y and x axes. And if I'm moving this function vertically, we'll say by 2. So if I move this function up by 2, all I'm going to do is move all my y values up 2. So I go up 1, 2, up 1, 2, up 1, 2. And my new function is just the same function moved up 2 units. I can also move them down by subtracting. So if I redraw my original function, I have 1, 2, 2, 1, 3, 2, and 4, 4, my original function. And all I'm going to do if I am trying to sketch my transformed function, vertically translated down 2, I just move everything down 1, 2, down 1, 2, down 1, 2, down 1, 2. And my new function is just the same thing, moved down 2 units. So I'm going to draw a line here, I guess I'll leave this here, and then I'm going to talk about vertical or horizontal translations next. And these similarly move left, or as you might guess, move left or right. What's a little bit different about these is first, since they're horizontal, all our horizontal transformations occur inside the function or inside with the x. So we're going to have f of x minus a in there, or our transformed function could be f of x plus a. What's also different about this is adding, in this case, moves left, and subtracting moves right. So while you would think if you're subtracting a number, you're moving it in the negative direction, whenever you have a horizontal transformation, it's sort of the opposite or inverse of what's happening. So if you are subtracting, you're actually moving it in the positive x direction. If you're adding it, you're actually moving it in the negative x direction. So though it's somewhat counterintuitive, but it makes sense if you go into the why of it, which we can talk about in class. But we're going to use the same coordinates to make for our original function when we're demonstrating our horizontal translations. So I'm going to start by sketching my original function. Okay, so I have 1, 2, 2, 1, 3, 2, and 4, 4. And we'll say that this one is moved 2 to the right. Sorry, I'll do plus 2. This one will be 2 to the left. So I'm going to do f of x plus 2. So this is actually going to move 2 to the left. So I'm going to go 1, 2. This one will be 1, 2, 1, 2, and then last 1, 2. And so my new function, if I'm adding, is moving 2 to the left. So everything has just gone 2 that way. Now I'll demonstrate if we moved it 2 to the right, we'd be subtracting inside of our function. So we have 1, 2. So I'll plot my original points. Same for as always. And now all I'm doing to get my transformed function is moving 2, 1, 2 to the right. 1, 2, 1, 2. So all I did to get my new transformed function is move 2 to the right. So those are translations. I'm going to flip the page and talk about reflections now. So reflections just flip or reflect over axes. So I'm going to, reflections generally, they flip or reflect, so that's kind of a circular definition, over axes. So the X or Y axis. So a vertical reflection, it reflects or flips over the x-axis. So it flips over the x-axis, and this is written as g of x equals negative f of x, so the negative goes in front. I want to make a quick little note. All you're doing here is negating y values. So you switch the sign on your y values, and that will give you your new function. So if we do our example with our same points, we have 1, 2, 2, 1, 3, 2, and 4, 4. If we graph the original function, we have 1, 2, 2, 1, 3, 2, 4, 4. All I'm going to do is flip it over the x-axis here. So I'm flipping it over this way, and I'm going to negate my y values, and then I will have my new function. So for 1, 2, I'm going to do 1, negative 2. For 2, 1, I'm going to do 2, negative 1. For 3, 2, I'm going to do 3, negative 2. And for 4, 4, I'm going to do 4, negative 4. And then I have my new function, or my vertically reflected function. Sorry. So it flips over the x-axis. Horizontal, you might guess, is going to flip over the y-axis, or from left to right. So for this one, it's going to be written g of x equals f of negative x. So it's written slightly different, and this one flips over the y-axis. And so if we do our example, as we do with the same numbers, 1, 2, 2, 1, 3, 2, and 4, 4, I'm going to sketch our original function. So I have 1, 2, 2, 1, 3, 2, 4, 4. All I'm going to do for this one to reflect over the y-axis is negate my x values. So since it's horizontal, we're just changing our x values. So instead of 1, I'm doing negative 1, 2. Instead of 2, 1, I'm doing negative 2, 1. Instead of 3, I'm doing negative 3, 2. Instead of 4, I'm doing negative 4, 4. So when I sketch my new function, it's just the same function reflected over the y-axis or on the other side. So that's our vertical or horizontal reflection. The last type of transformation we're going to talk about today is vertical stretches and compressions. And these are going to stretch and compress the graph, as is stated in their title, but all you're doing here is multiplying So all you're going to do is multiply y values by a constant. So you're just multiplying your y values by a number. For a stretch, you're going to transform or get your transform function by multiplying by a number greater than 1, whereas your compression, you're going to get by multiplying by a number less than 1. So our shorthand for this, if a is greater than 1, it's going to equal a stretch, or it's going to elongate and get taller. If a is greater than 0 but less than 1, so again, if it's negative, if it's less than 0, it would be a reflection. So if it's between 0 and 1, it's going to be a compression, or it's going to get flatter. So compressions get flatter, stretches get narrower. So it gets tall and thin if it stretches, it gets short and fat if it's compressed. And so let's show a couple examples of that. We're going to use our same key points. I won't rewrite them this time. But what we're going to do here for the stretch, try to leave us plenty of room. It goes up to 8, 1, 2, 3, 4. So I plot my original points. Here's my original graph. And for this one, I'm going to, if say my example was g of x is 2 times f of x, I'm going to multiply all my y values by 2. So I have 1 and then 2 times 2 is 4. So I'm going to plot the point 1, 4. 1 times 2 is 2. So I'm going to plot 1 or 2, 2. 3 times 2 is 4. So I'm going to plot 3, 4. And 4, and then 4 times 4 is 8. So I'm going to plot 8 way up here. So as you see, it gets taller and narrower when we have a stretch like that. If we do a compression, it's going to look a bit different. Label my axes. Here, if we plot our original points again, looks like that. But in this case, I'd have g of x is equal to, we'll say 1/2 f of x. So notice it's a number less than 1. And I'm still going to multiply this by my y values. But multiplying by 1/2, you should know or may know that it's the same as dividing by 2, since that line means dividing. So I'm actually going to divide all my y values by 2. So at 1, I'm doing 2 divided by 2, which is 1. And then 1 divided by 2 is 1/2, so it's going to be above there, but it's less than that one. 2 divided by 2 is 1 again, and then 4 divided by 2 is 2. So my new function is definitely flatter and closer to the x-axis, so that would be a compression. All right, I'm going to stop there for examples. I'll do a couple extended examples in another video, but that's all for now.